Greetings and welcome to part 7 of the calculus series. In this video, we'll be looking at how calculus can help us to solve problems involving increasing and decreasing functions. The success criteria for today would be for students to, firstly, determine the domain for which a function is either strictly increasing or strictly decreasing, and 2, to prove that a function is either strictly increasing or strictly decreasing for a given domain. So far, we have learnt about the concept of the derivative, that for any given function at any given point, the derivative will tell us the gradient of the tangent at that point. We can also call the derivative the gradient function. Using calculus, we have learnt to solve many problems, including those involving the normal to a point on a curve, as well as problems involving connected rates of change that we've covered in the last episode. We have also covered many rules, including the power rule that applies solely to power functions, as well as the general rules that apply to all functions. Let's try to understand the concept of a strictly increasing function. Observe that along this blue part of the curve, because the y value is increasing, the red tangent is always sloping upwards, meaning that it has a positive gradient throughout. So using calculus, we can say that the derivative will be positive. Likewise, if we look at this green section of the curve, it is decreasing and the tangent is now sloping downwards, so the derivative will be negative along this section. For completeness sake, let's look at this section as well. You can see that it is also decreasing and the dy dx, the derivative, is also negative. To summarize, if a curve is strictly increasing, the dy dx is strictly greater than 0. And if it is strictly decreasing, then the dy dx is strictly less than 0. Now let's solve some problems. Find the domain of x for which each of the following functions is decreasing. In part A, we have a quadratic fx equals to x squared minus 4x plus 9, and in part B, we have a cubic gx equals to x cubed plus 8x squared minus 35x plus 13. Pause the video here and give this question a good try. Firstly, for this part, we don't even need calculus. Because it is a quadratic, we can complete the square by splitting the 9 into 4 and 5. This allows us to factorize x squared minus 4x plus 4 into a perfect square of x minus 2 squared. So graphically, it will look like this, a happy quadratic graph that concaves upwards. The minimum point will be at 2, 5. From the graph, we can tell that the decreasing part of the graph is when x is less than 2. However, now that we do know calculus, let's try using it. After I differentiate, I get a derivative f prime x to be 2x minus 4. Since the function is decreasing, we want the part where f prime x is less than 0. So solving this linear inequality gives us x to be less than 2. You can see that these two different methods give the same result, and hopefully you can also see how much faster the calculus method is. So for one part B, we can't quite complete the cube, so we are forced to approach this problem via calculus. So graphically, the cubic function looks like this, and our aim is to find this portion of the curve where it is decreasing. So we'll differentiate gx, we'll get g prime x to be this quadratic, 3x squared minus 16x minus 35. Since we want the part that it is decreasing, we'll set g prime x to be less than 0. Fortunately, this quadratic can be further factorized. Graphically, g prime x is shown by this red parabola. It intersects the axis at minus 7 and 5 over 3. Now, which portion of the gradient do we want? We want this part which is below the x-axis, where the gradient is negative. So we can conclude that the portion of the graph is for x between minus 7 and 5 over 3. Problem number 2. Here are two more functions. Again, we want the domain for each of these functions, but in this case, we want the part where the function is increasing. So pause the video here and give this question a good try. So just to give you an idea of what we are dealing with, this is a sketch of the function, and we are looking for this highlighted part where the function is increasing. But even without knowing how the function looks like, we can still study the gradient. So what we can do is we can differentiate the function, and we're going to employ the quotient rule. So first we let u be the numerator, 2x plus 1, and v be the denominator, square root of 3x minus 1. So du dx is simple, it's just 2. dv dx requires the chain rule. So first we're going to get 1 over 2 of square root 3x minus 1. But don't forget, we still have to multiply by the chain. So multiply by the derivative of 3x minus 1 gives us a times 3. So now let's put it all together. So using the quotient rule, f prime x is going to be v du dx minus u dv dx over v squared. So this is what we're going to get. This is quite complicated. So what we're going to do is for the first term, the v du dx, we can make it the same denominator as the other term in the numerator. So let's simplify it this way. Now with a common denominator, we can subtract the two terms in the numerator together. We can simplify it. We're going to get 6x minus 7 over 3x minus 1 times square root 3x minus 1 in the denominator. Now, we are looking for the parts where the function is increasing, so we can set the derivative f prime x to be greater than 0. While this inequality may look daunting, note that we are given the fact that x is greater than 1/3. This tells us that 3x minus 1 must be greater than 0. And if you look at the denominator of the f prime x, that denominator is made up of 3x minus 1 and square root of 3x minus 1. So if 3x minus 1 is positive, then the denominator will also be positive, meaning that the only way the entire derivative can be positive is that it's a positive divided by a positive. So 6x minus 7 must also be greater than 0. Hence, the domain of x will be x greater than 7 over 6. Now in part B, since we have a product of two functions, let's employ the product rule. So we're going to set u to be x and v to be 2x minus 1 to the power of 5. So the product rule states that g prime x will be u dv dx plus v du dx, and we can differentiate them. This is what we'll get. And we can further simplify this by first noting that we have a common factor of 2x minus 1 to the power of 4. So let's factorize that out. And this is what we'll get. G prime x will be 2x minus 1 to the power of 4 multiplied by 12x minus 1. Since we want the increasing part of this function, we'll set g prime x to be greater than 0. Note that anything raised to an even power has to be positive. Therefore, for this gradient function to be greater than 0, 12x minus 1 must be greater than 0, so x must be greater than 1 over 12. Now, does this look correct to you? There is a mistake hidden here. Why don't you pause the video here and find it? So did you find the mistake? Well, it turns out that anything raised to an even power isn't always positive. It could also be 0. And this happens for this question when x is equals to half. So we have to exclude half from the domain. Therefore, the final answer should read x is greater than 1 over 12, but x cannot be half. Well done to you if you have spotted the mistake. Problem number 3. Show that the cubic equation y equals to x cubed minus 6x squared plus 15x minus 2023 is a strictly increasing function for all real values of x. Pause the video here and give this question a good try. Since we're concerned about the gradient, let's differentiate and get the gradient function. So dy dx here will be 3x squared minus 12x plus 15. Now we've come to a very common error. Some students tend to set this to be greater than 0 like the previous problems we have covered. But this is illegal. We're trying to show that this is positive, so you can't assume it's positive at this juncture. So what should we do instead? Instead, what we should do is complete the square. And that will give us dy dx to be 3 times of x minus 2 squared plus 3. Now we can go to some facts that we do know. So x minus 2 squared is greater than or equals to 0. Any number that you square has to be at least 0, so it will be positive or 0. And if we multiply that by 3 and add 3 to it, it will be greater than or equals to 3, and 3 is greater than 0. By that logic, dy dx will always be greater than 0. Hence, this function will be an increasing function for all real values. So these will be the steps we take to make this argument. So let's now turn back to the success criteria that we've set out at the start of the lesson. So are you now able to determine the domain for which a function is strictly increasing or decreasing? And are you also able to prove that a function is strictly increasing or decreasing for a given domain? So if you have any questions, please post it in the comment section below. With that, we've come to the end of part 7. Do look out for part 8, where we'll be looking at how to find stationary points, as well as apply the first and second derivative tests to determine their nature. Thank you for your kind attention and have a great day of learning.